All right, welcome back, everybody. This is MTED110, and today we are moving on to Chapter 5. This is Lecture 5A, and we're going to talk about using numbers in sensible ways. So let me go ahead and get the slides pulled up. This chapter is a little bit faster than the last ones, at least hopefully it should be. But this is a good chapter, again, to practice using numbers in sensible ways, meaning trying not to rely on algorithms when you can use number sense instead. So we'll talk a lot about that in this chapter. Okay, so some observations, and you'll see this yourself as a teacher. Students often become desperately dependent on algorithms when they've not explored our numeration system. So I've been saying this for many lectures now, right? Basically, if students are not comfortable with our numeration system, they struggle throughout, right? That's the whole idea. Um, you'll find students, or maybe even yourself, immediately resorting to an algorithm, even when the problem is simple enough to be solved without any algorithms at all. So some examples are things like this. If you see a student breaking out an algorithm to compute something like this, for example, doing something like 12 times 8, we don't want students to need to use a structure like this. We want them to be able to do it in a meaningful way, in a way that doesn't require them writing down an actual like symbol. This is a type of math problem that we can do in our heads. We just have to know about our numeration system. So for example, if somebody gave me this problem, I wouldn't break out the algorithm. I would say, oh, okay, well, 12 times 8 is the same as 10 plus 2 times 8. So I've got 10 eights and then two more eights. That's 80. That's 80 plus 16, which is 96. There you go, 96. All right. So notice I didn't really need an algorithm, and I could have done that in my head. I was like, okay, 12 times 8, that's 10 times 8, which is 80, plus 2 times 8, which is 16. So that's 96 total. Yeah, so here's the thing. The thing about this part here is that this is a problem. If students are resorting to stuff like this to compute 12 times 8, that's a problem. And I have this analogy here that it's like driving to the store, purchasing a high-end food processor, driving home, setting up the food processor, only because you needed to mix some flour and baking powder. You could have achieved the same result by just using a spoon, but if you don't know that that tool is there and you don't have that tool, you're never going to think to use it. If you're only ever shown how to mix things using a food processor, that's all you're going to know. And you're going to think that you need to go for the big guns when you do something like that, but you don't. Once students can see how numbers are represented in our numeration system, they can perform computations in meaningful ways, and that are very straightforward and make sense. And it just gives students freedom and flexibility, which is what we like. And then I've said this a bunch of times now, but algorithms can sometimes divorce students from comprehension, or at least obfuscate deeper connections and relationships between quantities. That word obfuscate means to make less clear. And that's what algorithms can do sometimes. They can make less clear the connections and relationships between the quantities that we're exploring. Um, so let's talk a bit about mental computation, because I'll tell you this, when people are doing mental computation and they do some like crazy stuff, they're not actually watching the symbols move around in their head. They're not going like, okay, 122 times 15 is, and they're not like doing the multiplication algorithm in their head or like in space and drawing it. That's not really what they're doing. They're breaking the thing up they're breaking the problem up into manageable pieces and then working with the pieces separately and adding them together at the end. Yeah, it often doesn't rely on algorithms learned in school, but a comfortable and robust knowledge of numbers and our numeration system. This is from the book. The book says one important advantage of practicing mental computation for children and adults is that it helps develop flexibility of use of numbers and properties of operations, and it gives us a sense of control over numbers. This is another one of those emotional components to mathematics, right? When you see a math problem, oftentimes you might feel like it has control over you. Or if the numbers are big or the numbers are messy looking, it feels like they have control over you. And we want to have the opposite relationship. We want to have control over the numbers. And the only way you can do that is with developing flexibility and numeracy and understanding our numeration system, et cetera, et cetera. Okay, so here's an example. I did 12 times 8. Let's do 12 times 50. So let's go ahead and just take a moment here. Let's have a Doran moment and just compute what is 12 times 50. Okay, let's work on this one together. So some of you might have went straight to something that looks like this. And if you did, that's okay, but that's the algorithmic way. So what we want to focus on in this chapter is doing such things without an algorithm, using our numeracy that we've developed over the last couple modules. Okay, so what is 12 times 50? Well, the way that I see it is this. I see it as 10 times 50 plus another 2 times 50. Or the way that I read this is, oh, I'm doing the number 50 12 times. I'm adding the number 50 12 times. What do I get when I add the number 50 12 times? I don't know. What do I get when I add the number 50 10 times? Well, that's going to be 500. That's an easy one, right? That's a benchmark. And then what's 2 times 50? Oh, that's 100. That's an easy one too. Now I can just add these up in my head, and it's 600. So 12 times 50 is 600. How did you do it? Think about it. And then after you've thought about it, talk out loud. Talk out loud and explain how you did this, how you did this computation. Because this was just how I did it. But there's lots of ways to do it. So talk with your group or talk with yourself and see how you did it. And we'll talk about some other ways to do it in a moment. Okay, let's move on. Here's one way to do it. I did not do it this way, but this is one way to do it. 12 times 50 can be broken up into a more granular product where the pieces, the factors, are smaller. It's the same as doing 12 times 5 times 10. And that's because 50 is the same as 5 times 10 right there. Okay, but for students that are good students that are good with multiplication and they have their multiplication facts memorized, a lot of them will realize right away that that has got to be 60. So really we're just doing 60 times 10, and that's 600. Easy peasy, right? All it takes was splitting it up into something manageable. All right, here's another way to do it. This is the way that I did it, actually. So I did it by recognizing that 12 is the same as 10 plus 2. And so I'm really doing 10 50s and then adding 2 50s. And this is exactly what I wrote in a previous slide there. And here's yet another way. So again, it's not that bad, right? or I shouldn't say not that bad. I should say it's more flexible and open than you might think. 12 times 50 is the same as 6 times 2 times 50, right? 12 is the same as 6 times 2 right there. But now that we've got that broken up, we can associate however we want, right? Multiplication is associative, like we talked about in a previous chapter. So instead of associating 6 times 2 first, we can associate 2 times 50 first. And we're going to get 100 over here. And then we've just got 6 times 100, which is 600. Yay! I think that's cool. I think that's really cool. Anyway, so anytime you're doing any multiplication, I encourage you to try stuff like that. Just try it. That's what this whole chapter is about, right? Just try it out. Try the mental computation. There's no rush, right? Okay, let's try this one. What is 147 minus 66? And what I want you to do is I want you to try to do this one in your head, okay? Try to do this one in your head. You thinking about it? You're working it out? Okay, now that you've worked it out, talk out loud about what you worked out. Talk out loud about the process you went through in your head mentally. See if you can explain it to others. Okay, now let's talk about it together. What is 147 minus 66? Well, I'll tell you one thing that I see anxiety when I look at that because I don't want to do the subtraction algorithm on that. Luckily, we don't have to. We don't have to. Let's see. How would I do this one? I liked the equal additions algorithm we learned a while ago. Maybe if I can make this subtraction a little bit easier, it'll make things easier for me. You know what I want to do? I want to try doing this. I want to try adding 40 or adding 34 to both the minuend and the subtrahend. So I'm going to add 34 to both. And the reason I'm doing that is because this over here is going to be 100. And then over here, 47 plus 34, I can do that pretty easily. Let's see, that's 77 plus 4, that's 81. So we've got 181 minus 100, which is 81. Done. That's all I had to do. I didn't do any subtraction algorithm. I just took the problem and shifted it to something easier, and then the answer was immediate. So that's one way you can do it in your head, right? What's another way? Let's see. What did you come up with? What do I have written here? I don't know. There's so many options. Let's see. Oh, it looks like I did equal additions here, but I didn't shift it nearly as much. Here I shifted it just up by 4. So I added 4 to both to make this number 70. And then I had 151 minus 70. But even here, 151 minus 70, too hard, right? I can't do that off the top of my head. And for me, it's because that 70 is going to drop me below 100. And for some reason in my brain, when I pass below the 100, that's when the math starts to it gets fuzzier in my head. Do you know what I mean? I'm sure it's similar for you, right? That's okay. That's okay. Just take a breath. The anxiety is natural. Take a breath, break it up into something smaller, smaller pieces. So rather than trying to subtract 70 all at once, let's subtract 50 and then subtract 20 after we're done. And that's much easier because when I subtract 50 from 151, I get 101. Not too bad. And now this one is much more palatable for me, right? Like my brain can see that one. 101 minus 20, that's 81 for sure. That's definitely 81. There we go. So that's the idea. That's another way to do it. So much flexibility. Let's see. Oh, this is another way to do it. So you could count up to 70. So this is actually a method that, what was that, student B did back in chapter 3, I think. Count up to 70, count up 4 to 70, then count up another 30 to get to 100, and then count up another 47 to get to 147. And then when you add all those up, you get the answer 81. So this is using the distance method, right? And I highly recommend you do this because I think it just makes things so clear. Let's think about this on a number line. Here's 66, and here's 147. There we go. Now, what's the distance between those two numbers? That's what this is asking. What's the distance between those two numbers? Let's see. So we can count up 4 to get to 70, count up another 30 to get to 100, and then count up 47 to get to 147. And then what we're going to do is we're just going to go and add those up. And we're going to have 34 plus 47. That sounds familiar, right? And that's where we're going to get 81. So that's another way of doing it. That's another way of seeing it. Helps me out a lot, I think. What did I do here? What did I do here? Oh, I did something, I decided to split things up by the place values. So look here, 147 minus 66. This is the same as doing, 140 minus 60, and then doing 7 minus 6. Well, 140 minus 60 is much easier for me to do. That's 80. And then add 1 to get 81. Voila, there it is, right? 140 minus 60, and then 7 minus 6. Now, getting to that point might be a little bit hard to follow. So let's see. Let me write it like this. Let me validate that this is correct. 147, or verify, I guess it works too, verify. So 147 minus 66 is the same as 140 plus 7 minus 60 minus 6. Actually, let me put an intermediate step there. There we go. So what I did was I rewrote 140 as 140 plus 7, and then 66 as 60 plus 6. And now what I'm going to do is just kind of commute things around. I'm allowed to do that, right? So we have 140 minus 60 plus 7 minus 6, and that's where we get 80 plus 1, which is 81. Lovely, right? There we go. So there's lots of ways to do this. And even though this seems like a lot of work, you might be surprised at just how much of this you can actually do in your head. If you think about it, like, okay, 140, it's 147 minus 66. Let's subtract things in a more meaningful way. 140 minus 60, what's that, 80. And then you have 7 minus 6, 81. And there it is. All in my head, right? Mental computation. So that's the idea. Okay, so what I want you to do now at home on your own with your group out loud, all that stuff, is I want you to compute these right now on your own. So just take some time and think about it. I feel like I need an actual writing emoji now. I need to put a little funny meme about writing. Hmm. Okay, and then after you've worked a couple of them out, or at the same time, I want you to talk out loud about what you're doing. Talk out loud about what you're computing. Talk to your group, talk to yourself, just talk out loud. All right, now let's move on here. Oh, I was going to compute some of those. I'll leave those for you to compute. Computational estimation. So basically, mental math is kind of what we were doing right here. If you want me to do some of these, I'll be happy to do them. This one's another interesting one here. Just think about that one, and we can talk about that in the collaboration meeting. But let's talk about computational estimation. So this is just simply the act of estimating a quantity when, sorry, estimating what quantity a computation will yield when it's not immediately obvious what the exact answer is. Just seeing like what it's going to be about. So this is an extremely important skill. And this is a skill that you learn. This is not a skill that you're inherently born with. So being able to estimate things like size and number, that's numeracy. That's a skill that you develop that we teachers teach our children and teach our kids as they go along in the math curriculum. Also, there's this fact. Sometimes a precise answer is not necessary, and an estimation will just be fine. You don't need to know exact values all the time. Sometimes you can just get close and it's fine. Moreover, sometimes a precise answer is not even possible. Yeah, so there are times where you won't get an exact answer because an exact answer is not achievable, and all you can rely on is a good estimation. So a good estimation is necessary in that case. And the way that you do this type of stuff, the way you do this type of estimation is with a well-developed number sense and a deep understanding of our numeration system, as I've been saying over and over. See, now it's like I'm a broken record. It's like I'm a broken record because it's the same thing over and over. So here's a good example. And this is one of those times where I want you to think about it, right? So let's have a thinking moment here. In this problem right here, where should the decimal point go on the right-hand side to make this a true statement? Hmm. Where would I put the decimal point? Hmm. Well, I think after some consideration, you'll realize that the decimal point should go right there, right between the 4 and the 0. And the reason is because this number is about 24, and this number is about 6, and division is how many times that number goes into that one, right? Or I should say how many times this number goes into that number. Well, 6 goes into 24 4 times, so this should be about 4. And that's why the decimal point should go right here. Now, the only way I was able to do that is because I understand the size of these numbers here, and I can visualize and think about the size of those numbers. And once I have that, that was an easy problem to solve. That's a skill that your students will develop that you have to teach them. Okay, so let's try to do this. Let's do this one together. Let's estimate the following quantities. Okay, start with the first one. Estimate 4,521 divided by 2,317. Just estimate. Okay, I'll tell you what I see. Let's see. I see that this is approximately, that's the approximate sign, by the way. Yeah, don't use an equal sign if something's not equal. Do not use an equal sign if something's not equal. I'm going to say that this is approximately the same as 4,600 divided by 2,300. And 2,300 goes into 4,600 twice. And that is actually equal. So notice here there's a difference. Here, this is an approximation because this is not equal to that. Definitely not equal to that. I just rounded a bunch of things, right? They're not equal. They're not the same anymore, but they are pretty close. They're approximately the same. Um, then, let me erase this here. These are actually equal. So that's an actual equality. 4,600 divided by 2,300, that is 2. That's equal to 2. So I don't need to use an approximation symbol there. Anyway, that's a pretty good estimation. It's about 2. I think it's a pretty good estimation also because I rounded this up and I rounded this down. So maybe that'll kind of cancel things out, right? Maybe. In the end, this is just an estimation, so it doesn't have to be exact. All right, so now let's go to the next one. So take a minute or two and try to estimate the next one, number 2 there. Okay, let's talk about it. I see something interesting here. I see that 79 and 84 are pretty close to each other. Might as well just consider them as like canceling out because we're doing subtraction, right? So I could say that this is approximately equal to 9,079 minus 779. So what I'm doing is I'm just rounding 84 down to 79, and that makes the subtraction really easy, right? Just like we were talking about before, I can subtract 79 and then I can subtract 700, and I'm going to end up with 8,300. And that's an approximation. Not the exact answer, but a pretty good approximation. And in fact, I'm not very far off if you do the exact calculation. Okay, now let's go to the third one. So just like before, I want you to take a couple minutes and estimate 36 times 55. Estimate. Okay, I think I have my estimation in mind. I was trying to play around with breaking it apart. I was like, okay, maybe I could think about it as 30 plus 6 times 50 plus 5, and maybe I could do the foiling, or maybe I could do something like that. But then I remembered I'm just estimating. I'm just estimating here. I don't need to get anything so precise. So I ended up just deciding to round some things to something nice. So I said that this is approximately 40 times 50, and 40 times 50 is what? 2,000. Is that right? 40 times 50 is 2,000? Yeah, okay. And again, this is just an estimation, just an estimation. Doesn't have to be precise, doesn't have to be exact. And I'm sure that a few of you, many of you probably estimated this differently, and that's totally fine. I actually thought about rounding this to 60 and getting 2,400 instead. That would be another estimation. But the reason I decided to round down here, or sorry, the reason I decided to round down there is because I rounded up here. And I was like, maybe if I round this factor down and round this factor up, it'll kind of average out, right? Well, let's see what some students did instead. Okay, so the actual answer, the exact answer, oop, dropped my pencil. There we go. The exact answer is 1,980. So here is some students' way of estimating this product, and they explain it to us. Joe rounded to 40 and 60 and got 2,400. That's exactly what we just talked about, right? Irabeel said first round down to get 1,500, then round up to get 2,400, and then it's got to be somewhere in the middle because he rounded both down and then rounded both up. So a little bit past, I'd say 2,000. That's a clever way of doing it, and that's a valid way of doing it. That's a way to estimate. Let's see, Jen May said rounding both up would be too big, so I'll round 36 to 40 and then 55 to 50. That's what I did. So I did the same thing that Jen May did here and got 2,000. Notice this is pretty close. It's pretty close. The exact answer is 1980. Let's see, Izzy said a little more than 36 times 50, which is 36 times 100 divided by 2, and that's 18 times 100, which is 1,800, and it's about 5 times 36 more, which is 180, so I'll say 1980. So Izzy actually got the exact answer, and that's because she went ahead and started splitting it up in a meaningful way and got the exact answer. So she split this up as, she rewrote 50 as 100 divided by 2, and then was able to use her understanding of the numbers to move things around and do 36 divided by 2 times 100 to give her 1,800. That is valid. That is actually a valid method of computation. I encourage you to verify it. See if you can write a string of true equalities that shows Izzy is correct in doing that. In particular, see if you can show that this is actually equal to this. Are those equal? Think about it. Try it out. All right. Debbie said rounding both up gives 2,400. That's too big. I'll say it's about 2,200. She just threw out a number. Not bad. Cambiz said a little more than 6 times 6 times 50, which is 6 times 300, which is 1,800. So I'll say 1,900. There you go. Pretty close, right? So every single one of these, is that all of them? Yeah, every single one of these is is a valid method of estimation. So your students are always allowed to do that. And we have to encourage them that they're allowed to do that when we're just looking for an estimate. All right, so percentages in particular is an extremely important skill. We use percentages a lot, a lot, a lot, a lot. So let's talk about it here. And let's just start with an example. Here's a nice example, right? A $148 coat is on sale for 30% off. About how much is it after the discount? Think about it for a minute. What do you think? What's it going to be? Estimate, estimate, estimate. Doesn't have to be exact, estimate. Okay, let's talk about it. The idea is this. 30% off of 148, I don't know. But the one thing that's nice is that now that I know about numbers and I know about our numeration system, I know that 30% is the same as 3 times 10%. 10%. So 30% is 3 10%. Well, how much is 10% of 148? How much is 10% of 148? Well, 10% of 148 is 14.8. 14.8. And in some senses, I just moved the decimal point, right? Why is it that multiplying by 10% is moving the decimal point? Well, that's because 10% is 1/10, and that's just multiplying, or I should say dividing by 10. And that's why this ends up getting moved back by one decimal place. So 10% is 14.8, but that means that 15 is approximately 10% of 148. Sorry, lost my train of thought for a minute there. Okay, so 15 is 10%. So that means that 3 times 15 is 3 times 10% of 148, which is 45%. Of 148. So it's $45. So $45 is 30% of 148. So how much is the coat going to be after the discount? About $100, about $103. So I'll say about 103. That's the answer. About $103. Okay, and that's all it really takes. So the key thing here is stuff that we've seen a whole bunch of times before, right? I took 30% and thought about it in something smaller. I thought about it in smaller terms, I should say. I thought about it as 3 times 10% and then applied that 10% 3 times, which is much easier, right? So that's one of the ways you can do this. Yeah, there you go. So the code is about 105. 105. Actually, I should have written 103 right there. That's all right. It's an estimate, right? It's an estimate, so we're not looking for precision. Oh yeah, so here you go. The actual answer is 103.60. So my estimate of 103 in the previous slide was very, very close, only 60 cents off. How about this one? So I'm sure you'll do this at some point, right? You're looking for a hotel room and you found a hotel that charges $150 per night plus 16.4% tax. About how much will one night cost you? Well, let's pretend you're on the phone making this phone call right now and they're throwing out a lot of numbers, or maybe you're looking at a bunch of stuff online and comparing a lot of prices and you're like, okay, what is, you don't need to use a calculator. Just get an estimate, right? I mean, if you're going to get a hotel room and you're already talking about spending this amount of money, if you're off by a few dollars or even like $10, it's not going to be that bad, right? So let's see. I would say this, 155, this is approximately 150. And 16.4, that's approximately 16%. So what we really need to do is find 16% of 150, and we'll be pretty close. So how can I do that? How can I do that? Well, the same way we did it before. We're going to split 16% up into something more manageable. 10% plus 5% plus 1%. And honestly, anytime you're trying to estimate any percentages, if you can find these 3 values of the number that you're looking for, or of the thing that you're applying the percentage to, then you can find basically any percentage really easily, almost in your head. So like, what's 10% of 150? Let's fill it out. 10% of 150 is 15. Okay, but 5% is going to be half of 10%. Let me write that, half of 10%. And 10% is 15, so half of that is 7.5. And now here's the other cool part. 1%, 1% is 1/10 of 10%. So it's, I should say 10% of 10%. Is that right? 10% of 10%? Anyway, it's 1/10 of 10%. Oh yeah, so not quite, not quite. And that's going to give us 1.5. Okay, so now we have these critical values. We know how much 10% is, it's 15. We know how much 5% is, it's 7.5. We know how much 1% is, it's 1.5. So if we needed to find 16%, we can just add all that up and we'll be pretty close. Let's see, what do we get? Plus, let's see, 15 plus 9 is 24. So it should be approximately $24 in tax. So the question, this is where you got to stop. See, I was just about to dust my hands off all the way back to like chapter 1, all the way back to chapter 1. I was just about to dust my hands off and say, answer is 24. But we got to remember what the question asks. We have to look back. We have to look back, and the question says, how much will a night at the hotel cost you? That's what we really want to know. How much money are we going to spend? Well, it's going to be 155 plus 24 approximately, right? So let's do that over here. 155 plus 24, that's 179. So it should cost us about $179 to stay there for one night. Now 180, right? So might as well round up and be safe. Notice rounding up here is not a bad idea, because if you round up, then you're not going to undershoot the cost, right? The worst thing is you don't want to walk up somewhere with the money in hand and then you find out you don't have enough, right? It's better to overshoot. All right, but again, this is just one way of estimating it. I think I have a different one written down next. Let's see. So in this case, I rounded up. Let's follow along here. 155 is about 160. So I rounded up there. Probably the safer bet, right? 16.4 is about 16%. 16.4 is about 16%. So now I'm kind of balancing things out a little bit. And then I went through, okay, so 10% is 160. So 1%, 10% is 16. So 1% is 160. So 6% is 960. Therefore, 16% of 160 is 16 plus 960, which is 2560. So the hotel room will cost about that much. There we go. About $180. There we go. Actual answer, 180.42. So even my previous estimate of 179 was, yeah, 179. I was only off by less than $1. I was off by less than, oh no, I'm sorry, not less than $1. I was off by $1.42. That I think I could scrounge if I'm getting a hotel room for 155 bucks. I can find an extra buck somewhere, Okay, so estimating with percentages is really fun. It's really straightforward. It's what do I want to say? One last tip about this. Funny enough, because it involves tips. At least in the city of Long Beach, the sales tax is 10% now. I think it's a little bit higher than 10%. So what's nice is if you order some food from a restaurant, right? You have it delivered, or you go over, you pick it up, bring it home, and you wanted to leave a tip. Well, what you can do is you can look at the actual price. Like maybe the price of your meal was $34.60 or something, right? And you want to know how much you should tip. Well, if you want to give them 20% tip, one thing you can do is you can move the decimal point and think about the quantity 340. Well, 340 is about 10%, or maybe we just say 346. 346 is about 10% of 3460. So if you double that, you're going to get 20%. So 20% is about $7. So if I double that, 20% is about $7. So if you wanted to know what to tip them, you would give them 7 extra bucks. There you go. So it's a nice like tip for how to tip. Okay. I've said this before. This is a skill that we help early learners develop, is how to estimate quantities. So for example, how long is a foot? How long is a foot? Like I don't even think, maybe I don't know, like maybe my own foot, right? Like maybe that's about how long a foot is. How do you have an intuition? How do you have an intuition for how long a foot is? Well, you get exposed to it, and somebody points out that that's how long a foot is, and this is not how long a foot is, and so on and so on. That's a skill that we math teachers help our students develop. Or how about how wide is this room? Can you estimate how wide your room is, the room you're in now? You can probably get a pretty good estimate because you learned that as a child. How many people could fit in this closet? This is a closet right here. How many people could I fit in that closet? Well, I could probably estimate it if I imagined the space in there and I imagined the size of a person and I thought about stacking them in there, right? And I could do that because that's a skill that that was developed early on. And then what you can do is you can extrapolate. How much space would 10,000 people take up? Imagine 10,000 people. It's hard, right? The numbers get harder to understand or harder to fathom, really, once they get that large. So try to visualize this instead. Visualize three people. So close your eyes and just imagine three people around you for a minute and think about how much space that is. All right? Now, now try to imagine 30 people. So imagine that group of three and multiply that by 10. So now imagine right around you, you've got 10 of those groups of three. Okay, think about how much space 10 groups of three take up. Okay, now imagine that it's 10 times that. So maybe if you're imagining these 10 groups of three, these 30 people around you, now imagine 10 times that amount. It would be like 10 times more, right? It'd be like 10 times more of what you're looking at right now. And that's 300 people. And then you can extrapolate. Multiply that by 100. Multiply that result by 100, and that's 30,000 people. And there you go. And that gives you kind of an estimate for how much space 30,000 people can take up, or 3,000, or 300,000, and so on. So this is a good thing to do to help visualize these things and estimate them. And this is one of the skills that we'll teach our students. All right. Oh yeah, notice how number sense was used to facilitate understanding these. If we teach students about number sense, we teach them about units and create an environment that supports using these ideas. Then we help them to develop these incredible tools and life skills. There you go. SMP number 7, reason abstractly and quantitatively. And obviously there are countless real life applications to estimating quantities, countless. I can't even count how many. That's why I said countless, right? All right, so let's play. Let's take a look at activity 5A. If I remember correctly, this one is quite short because it's just really about estimation. Let's pull it up and take a look. Okay. There we go. Estimating quantities. So the first question says this. It says to estimate the following quantities and describe precisely the process you use to compute the estimation. So I don't want you to just come in here. Oop, sorry. There we go. I don't want you to just come in here and write the answer like, oh, I don't know, 10,000 or something. Like that's not sufficient, right? You need to explain how you got that estimation in words. Write a sentence. That's why you have all this space right here, right? You got all this space. Write a sentence explaining how you got your estimation. And you're going to do that for each of these. Each of these. And that's it. That's pretty much it. So some of them are percentages, some of them are not percentages, but you do have to explain how you got that estimation. All right, so I think that's going to be it for today. Yep, that's pretty much it. Okay, thanks again for tuning in, everybody, and I will see everybody next time.